All right. Samantha. Easton.
Here.
Here's Easton. Garrett. There. Nolan. There. Benton. There. Jenna. Rylan. Mateo. Here he is. Okay, Gabby. Gabby, right there. Gabby, back there. Okay, cool. Charles, here. Lizzie, back there. Brandon. Ellis. Kate. Arisha. Carter, back there. Abigail or Abby, right there. Clayton. Clayton. Here. Noah. Here. Yvette. Logan. There. Angel. Here. Sydney's here. Wyatt. It's right there. Cannon. Over there. Mustafa. Callie. It's not gonna be good. Emily's here. Liam. Over there. Cameron is here. Jamie. Jamie is and Evans. It's right there. All right. How's everyone doing today? Somewhere on a scale of here to here. Just doing at least okay. It's cold. I like the cold weather. Cold weather is good to me. Yeah, I haven't graded the worksheets yet. That's completely my bad. I've been really caught up on my research. I don't know if y'all know what the side effects of steroids are, specifically prednisone, but it's medically induced insomnia. So I've been sleeping like 2 hours a night. That being said, I've been extremely productive with my research. So I've written a ton of stuff over the past 2 days. I've done like, let's see, yesterday, I went, or not yesterday, I guess the night before last, I went to bed at 12:30, woke up at 3:30, and then did like 5 hours of research before I had to get ready, which was like super nice. Wait, yeah. I was just marked. Oh. So I got like 5 hours of research done then, and then yesterday went to bed a little earlier because I was tired because I had no sleep, and I woke up this morning at like 4:30 and did a bunch more research too. Been very productive. I don't recommend it though. I feel absolutely awful. I feel like I've slept 6 hours in 2 days. I don't recommend it. So, so I'll get those worksheets graded soon. I don't know if y'all heard. I think it's class Wednesday. I was trying to announce it. No quiz today. It says in the schedule quiz today. The other sections are a little behind. So we're all going to have the quizzes on Monday. So that allows us to dig into some of this 8.1 material. On Monday before the quiz, we'll do a little review for it though. So, right about there. Any questions about anything? While I'm at it, I forgot to open up the homework for 8.1. So let me open that up. Is anyone having any problems with the homework or anything like that? Looks good. Yeah, you are. Reason right through it. Don't forget you have 7.4's homework is due tonight. We finished that on Wednesday. Where's my assignment? Yeah, there's two 7.4 homeworks. Part of it goes over permutations and combinations. Another part of it goes over probability applications. Let me open up this 8.1 homework, and I'll set it to be due. I can do next Wednesday. How about that? I can look at that. That's the 4th. Cool. And if you have any problems with any homework, like access or anything, text or email me, and I'll try to get that out. Another thing, I recorded our team meeting is class on Wednesday, but I didn't record it because I'm silly and I didn't think about that. I'm going to record them from now on. So if you want to look back on them, you can. I'll probably just start uploading these to my YouTube channel, and it'll just be in a playlist. None of y'all are in the video, so you don't have to worry about that. And I also don't have to worry about like having y'all sign anything. So cool. I think that's all I have to yap about. Any questions about anything at all from you guys? All right. So what have we been talking about over the past 2 weeks? We've been talking about how to abstractly group things together in what we call sets. So a set is just a collection of objects, or we can talk about if an object is in the set or not. We talked about different ways to put those sets together, counts of the items in those sets, and everything like that. Then we move to different ways of counting, right? So a bunch of possible outcomes, how we would count up certain things like that. For instance, one of the things we counted was how many possible hands there are that have 3 kings and 2 aces, or 3 aces and 2 kings, whatever it was. We went through and we computed that using combinations and permutations. Now we're going to talk about how to use those in probability. So what we're going to talk about is what we call the event or the sample space, some events and some probabilities. A lot of words on this page, so I'll just sum them up. A sample space is all possible outcomes we want to consider. For instance, when we were talking about 5 card hands that we can construct, the sample space for that is all possible 5 card hands, right? And so the way we would construct that is that would be 52 choose 5, right? It'd be choose 5, not permute 5, because it doesn't matter the order. If I get the ace, 2, 3, 4, and 5 of hearts, it's the same thing as if I got them in a different order. So we don't want to. And so the way we define the probability of getting a certain hand is all the ways we can get that certain hand divided by all of the possible hands. That makes sense. A really simple example of an event space is rolling 1 die. A die has 6 sides, so your event space has 6 elements in it. The 1, 2, 3, 4, 5, and 6. So they're the things you can roll. So for instance, what are the odds that you roll a 3 when you roll a die? Can anyone?
1 out of 6.
1 out of 6, right? There's one way to roll a 3. There's 6 total rolls. And so the probability that 16.7% is the probability. I love doing that. I'm such a child. Like I was at a lecture yesterday. We had a guest lecturer from St. Louis University talk about her research. And she's like, yeah, I've been doing this for about 6 or 7 years. And in my mind, I was like, such a child. It's so funny. It's not funny, actually, because I went out to Culver's a little while ago, and there were like six-year-olds, maybe 5-year-olds, and they just kept going 6, 7 to their parents, but really loudly. And I was like, I'm gonna blow my brains out in the Culver's right now. I'm gonna change these kids' lives forever. They won't shut up. This is terrible. So yeah. Has anyone ever played the game Catan? Catan is a popular board game where you have lands and you control resources to build things. On each of the little tiles, you put a number, and that number has dots below it. That dot represents the probability that you roll that number. So you have 2 dice. The most likely number to roll for 2 dice together is 7. That has the most possible combinations. There's 5 different ways I can do that. 6. One of those. Then all the other tiles list all the other possible ways you could roll it. So out of 2 dice, there's 12 possible outcomes, and 7 is the most likely. It's about half the time you should expect a 7 to be rolled because it's so likely. Yeah. So we'll talk about all that sort of stuff. And we'll go through some examples that help to concretely put this together. But this isn't really that difficult to grasp, in my opinion. As long as you're cool with the combinations and the permutations, figuring out probabilities is pretty straightforward. Any questions about anything? Also, if you haven't played Catan, you definitely should try to play Catan. It's like one of the easier nerd board games, in my opinion. All you do is you collect resources, and you build houses and cities and roads, and you piss your friends off, and it's great. So much fun. I have like every expansion of it because my wife and her sisters love to play Catan too. But board games are fun. Cool. All right. So I talked about all this info on here. I summed it up so we don't have to read all of these words. For example, we want to write out the sample space where two coins are being tossed and we're observing whether they land on heads or tails. What is the sample space here? It's a little interesting. There's 4 possible outcomes here. They both land on tails. They both land on heads. One's on heads, one's on tails. One's on tails, one's on heads. So there's a sample space of 4 possible outcomes. So I'll let my sample space, maybe I'll call it S. And I'll write it as a collection like this. Tails, tails. Heads, heads. Heads, tails. And tails, heads. Notice that these aren't actually the same thing, right? They're 2 different outcomes. There are exactly 4 possible outcomes. 2 of them look the same, because if I move the coins around, they are the same, but they're different outcomes because they both contribute to the probability. So for example, if it says find the probability that at least one toss is a head, if both of these were tossed, well, how many of these have heads in them? 3. So there's 3 with heads over 4 total possible. That's equal to 3 over 4, which is 0.75. And who remembers how to turn a decimal into a percent? Multiply by 100. So that's just 75%. A lot of these numbers, I can look at it and I can tell you 0.75, that's 75%. Or 3 out of 4, that's 75%. So the odds of flipping at least one head is 75%. What that means on the contrary is that the odds of flipping no heads is 25%. And so that's another thing we'll talk about, is the probability of something not happening is 1 minus the probability of it happening. The probabilities have to add up to 1. It says write out the sample space. An experiment consists of tossing a coin twice and observing the number of heads that appear. So we're talking about the number of heads that appear. What are the possible outcomes? I could have 0 heads appear. That's 1. I could have 1 head appear. Or I could have 2 heads appear. Those are the possible events here, the number of heads that get rolled. There's 2 ways I can get 1, but the sample space, this set, we don't count the same thing. But note, there are 2 ways to get. Now it says to write out the sample space of 3 coins are tossed and observing whether the coin falls in heads or tails. Using a tree will help with this. Cool. So 2 coins are tossed. I get, well, for the first toss, I can get 2 heads, a head and a tail and a head, and a tail and a tail. From each of these, I then get the same next 4 possibilities. 1, 2, 3, 4, 2, 3, 4, 3, 4. And these are all the same. Head, head, tail, tail, head, tail, tail, so on and so forth. I don't want to write all this out. So we've got 4 here, and we've got 4 times 4. Can anyone guess what the next row is going to be? How many options will be there?
16 times 16.
Close. It's just going to be 4 times 4 times 4. So 16 times 4. Each of these splits into 4. And so on and so forth. So I have a ton of different options. And so the sample space is going to have 4 times 4 times 4, 64 possible outcomes. There's quite a few outcomes. It says find the probability that exactly 2 heads appear if 3 coins are tossed. So what I've just realized is that I wrote out the sample space wrong because I wrote out 2 coins being tossed 3 times in a row and not 3 coins. So ignore all of that. This is why reading is important. 3 coins are tossed. So there's heads, 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 tails, heads, 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 tails, tails, heads, heads, tails, tails, heads, tails, tails, tails. Let's see the first one being heads. Means that this one could be heads or tails. So if I could also get a heads, tails, tails. So maybe I'll use a scratch paper here. Again, completely on me because I didn't actually read. So do it here. The first one is heads. The second one and the third one. The first one is heads. Then my possible outcomes are heads, heads, tails, heads, 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 tails, heads, and heads, tails, tails. And if it's tails, I get tails, heads, heads, tails, heads, tails, 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 heads, and tails, tails. And I believe that's all of them. I think this is right. Yeah, because that can be heads or tails. And then that could be heads or tails. Yeah, okay. So this is the sample space. And maybe I separate these. These are all of the possible outcomes. And so there are 1, 2, 3, 4, 5, 6, 7, 8 outcomes. And it says the probability that exactly 2 heads appear. Well, so how many of them have 2 heads? This one has 2 heads. This one has 2 heads. This one has 2 heads. This one. Okay, so 4 of them. 4 have 2 heads. Let me move this up. Over the 8 total. And that's a 50% chance. So there's a 50% chance that I toss at least 2 heads. It means there's also a 50% chance that I toss at least 2 tails. And that kind of makes sense. I'd either have to toss at least 2 heads or at least 2 tails, right? That makes sense. If I don't toss 2 heads, then I will have tossed 2 tails, right? If I only toss 1 head, then I have 2 tails. If I toss 0 heads, then I have at least 2 tails.
This is exactly 2 heads, so 3 heads.
Good point. Yes, exactly. Thank you for pointing that out. So heads, 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 which I didn't even write down heads, heads, heads for some reason. I didn't consider that, I guess. So there's 4 out of 9, I bet. 9 possible outcomes because heads, heads, heads is an outcome. And again, you could do this as a tree. Yes. That's probably what my issue was. Thank you. There we go. So there are 8 possibilities. I'm super sorry. And we're wanting 3 of them. And 3 out of 8, yes, 37.5%. 7.5%. Again, an easier way to write this out would be using a tree diagram. So I got heads and tails for the first coin. From that, I can get heads, heads, or heads, tails. From this one, I can get tails, heads, or tails, tails. And then these each have their own options. Heads, heads could give me another head. It give me another tail. Head, tail could give me head. Head, tail, tail. Tail, head, head. Tail, head, tail. And then, oh, it should be tail. Tail, tail, head, tail, tail, tail. So that's how you would like use a tree diagram to list all these out, which is what I should have done in the first place. So I apologize. Cool. Then we notice there's 8 possible outcomes. As Nolan pointed out, we want exactly 2 heads. That's this one, this one, this one. So 3 out of 8 have 2 heads. Cool. A little bit confusing when I mess up the problem like 4 times in a row. So I apologize. If that problem wasn't clear, again, I'm recording this so you can go back through and watch. And maybe when you go back through and rewatch, if you do, point out the mistakes that I make, because that will help you. Yes.
Where are the recordings at? You said on your YouTube?
Yeah, once the recording is stopped, I'll upload it to my YouTube.
What's your YouTube channel name?
At Jackson Lewis at. I'm pretty sure that'll bring it up. Find out. Yeah, at Jackson Lewis Math. This is my channel. It's me graduating. Oh, yeah. Oh, because it's on my laptop. This is my channel. The user picture is me graduating. And then the banner's some math I was doing. All the videos in here are from me teaching business calculus. So if you want review for business calculus as well, it's in there. So again, at Jackson Lewis Math, if you just type that in the search bar, it'll pop up on the channel. So we said there's 37.5% here. Next one says find the probability that all 3 coins show the same if 3 coins are tossed. Well, we saw that there were 8 outcomes possible. How many ways are there for all 3 coins to be the same? 2. They can either be all heads or they can be all tails. 2 all same, which is 1/4 or 25%. So you have a 25% chance of tossing all 3 coins the same way, which is pretty interesting, in my opinion. But that makes sense, right? The odds are 1/2 each time. 1/2 times 1/2 times 1/2 is 1/8. So each outcome has 1/8 chance of happening. And then there's 2 chances we're looking at, so 2. Next example, we're listing the number of items in a sample space. So if I toss a coin and a die, how many outcomes are there? There's 6 outcomes for the die, 2 outcomes for the coin. All the possible combinations is the product of these together. Remember, all possible outcomes is the product multiplying the individual outcomes. Like if I'm picking out outfits, I have 3 shirts, 4 pairs of pants, 12 total outfits. This one has 12 items. Cool. The next one says selecting 3 cards in order without replacement from a deck of 52 cards. Well, so how many options are there? There's 52, we're doing without replacement, times 51 times 50 items. So there's a lot of items there. That's a decently large number already. That's either 75,000 or 750,000. 5 times 5 times 5 is 75. 0, 0, 0. So yeah, about 75,000 outcomes, a little more than that, maybe 77,000. A lot of outcomes there. So getting exactly one hand of 3 cards is pretty slim chances. Now it says selecting 2 cards without replacement in any order from a deck of 52 cards. This one might be meant to trip you up, but it's the same thing as beforehand. Without replacement means I have 52 options for the first one. I didn't replace it, so I have 51 options for the second one. So saying in any order doesn't change the sample space. It would change the probability of getting a certain hand, right? If my odds are I wanted to pick an ace and then a 2, that slims down the chances. That gives me 4 and then 4. But just in general, this is the odds right here. So note that that didn't change anything right there. Example 3 says there's a group of 100 people, of which 55 are male and 45 are female. Find the probability of event E where female is chosen. Well, there's 100 total people, and 45 are female. 45 over 100 is just 45%. So if I randomly selected a person out of that group, it's a 45% chance that she's a female. Cool. That was a pretty straightforward example. I'm kind of confused as to why it's so far in there, because the examples beforehand have seemed significantly more complicated than this. It's like really easy. This is one of the most popular examples when we do probability, is specifically picking balls from an urn. I don't know who uses urns for anything other than ashes, but it's like a metal vase. Like that's all an urn is. Like they used to just call all vases urns. And for some reason we use urns. I like the example of marbles in a bag a lot better because it seems a little less morbid, but we'll go with balls in an urn for now. So it says a ball is picked from an urn with 3 red, 2 green, and 5 yellow balls. How many total balls are there? 3 plus 2 plus 5 is 10 total. So I'll make a note of that. It says, what are the odds of doing this? So what are the odds that we pick green? Well, there's 2 ways I can get a green, because there are 2 green in there, over the 10 total. Oh, so that's 20%. Everyone with me on that one? That one's really straightforward. Then the odds of picking yellow. There's 5 yellow over 10 total. And that's 50%. And then not picking green. So how many of these are not green? That's going to be the red and the yellow together. That's 8 not green over 10 total equals 80%. And what do we notice? The odds of picking not green plus the odds of picking green are 100%. And that makes sense. It's like the example of the group split by male, female 2 ways. There's a 100% chance that I pick someone that's male or female from that group if that's the only way they're divided, right? For instance here, if the group is divided into these colors, either I pick a color that's a specific color, or I don't pick that color. So either I pick green or I don't pick green. Those odds have to add up to 100%. There's a 100% chance I pick a ball if I picked a ball. Here it says picking red or green. That means we add up the probabilities. So there's 3 red plus 2 green for 10 total is 50%. That's red, that's green. Then it says picking a green or a yellow. There's 2 green, there's 5 yellow, 10 total, and that's 70%. There you go. So fairly straightforward examples, but that's how we go through picking the probability of something happening, is we take all the ways that it could happen over all the possible outcomes in general. Now we've got an actual physical example. So suppose 211 CEOs were surveyed about their company's industry type and geographic location in the United States. Suppose that further that the CEOs were allowed to choose only one type of industry from these 3 choices and one geographic location from these 4 choices. And it says find the following probability to two decimal places. So we're going to have our calculators. It says find the probability that a CEO's response was that their company was not in communications. So we add up. What I want to do is I want to add up all these rows so that I don't have to go through and keep adding them up and give me my numbers there. So I just want to add up all the rows and columns real quick. Let's see, I'll add up manufacturing, 14 plus 16 plus 25 plus 14. Oh, that makes sense if I type in the right number. 14 plus 16 plus 25 plus 14. Right there, 10 plus 24 plus 25 plus 27. Here's 86 there, and 21 plus 7 plus 5 plus 23 is 56. All of those should add up to 211. And then I want to add up these columns. 14 plus 10 plus 21, that's 45. And again, I'm only doing this so that I don't have to keep adding them up for each example. I have all the numbers very cleanly listed for me. 16 plus 24 plus 7, 47, 25 plus 5, and then 14 plus 27 plus 23 is 64. And again, all of those numbers will also add up to 200. So now when I have to answer a question like this, I have the number pointed out for me right here. So for instance, the probability that their answer was not communications. So that's going to be everything that's not communications. So it's going to be 69 plus 56 all over 211. Calculator. 6 divided by 211. And that gives me 59.24%. It says response that the company's industry was in manufacturing or in the Northwest. Yeah. So I've got Northwest. And I've got manufacturing. And what do we remember about talking about the union of two things together? When we talk about them together, like if I took this number plus this number, I'm counting 25 twice. So I have to exclude 25 once. So this is going to be all the manufacturing plus all of the Northwest minus what overlaps between them, because I counted it twice. I counted it in this number and I counted it in that number. This is all over 211. Plus 55 minus 25 divided by 211. And that's 46.92%. Now it says the CEO's response to the company's industry was manufacturing and in the Northwest. So that's going to be where those two overlap. That's just the 25 to 11. And this is 18.85 or 11.85. So given a table like this, that's how I could find the probabilities that if I randomly selected one person, this is called a random variable. If I randomly selected him, I would get that response. Any questions about this? And again, this is built off of what we did with sets. When we considered the union of sets and counting them, we had to take out one part of their intersection because we counted it twice. We also now have an example with a standard deck of cards. A deck of cards is a really popular thing for probability because there's a lot of options and a lot of things we can do with it. Plus, gambling is very, very fun. It says from a deck of 52 cards, find the probability of these certain things. How many jacks are in a deck of cards? 4. And there are 52 cards in a deck. This is 1 out of 13, which is about 6%. It's or 7.6. Well, 7.69%. That's something to remember about decks of cards, because more than likely quizzes will involve questions about deck of cards. There's maybe a hint. I'll probably make a question on Monday's quiz about a deck of cards. It'll be an easy question, though. It'll be something like this. So there are 4 suits in a deck of cards: clubs, spades, hearts, and diamonds. Each suit has 13 cards, ace to king. There are face cards, jack, queen, and king, that are included in that. All the rest of them we call number cards. Ace is a number card, even though it's kind of weird. There are 2 colors, black and red, and there are 4 of each card in a deck. So that will be important. It says probability of picking a black card. Well, there are half the deck is black, so I could very easily just say the probability is 1/2. But more specifically, there are 26 black cards over the 52 total, which again is 50%. Right. Black has 13. 13, those add to 26. Red also has 26, if you're so inclined. And then the odds of picking a 2 or a 3. Well, how many 2s or 3s are there? There's 8. It's going to be 8 out of 52. 8 divided by 52 equals 15.38%. We can similarly answer these. The odds of picking a heart, well, the heart is one of 4 suits. So either I could say this is 13 out of 52, 13 hearts out of 52 total cards, or 1 suit out of the 4 total. These both equal 25%. So there's a lot of different ways that you could answer the same question, especially about a deck of cards. Picking a red ace, there's 2 red aces, ace of hearts and ace of diamonds. So that's 2 total cards out of the 52 possible, and that gives you a chance of 3.84%. And then not picking a face card. So it says here what your face cards are. So the probability of not picking a face card, instead of counting up all this stuff, is 1 minus the probability of getting a face card. Prob of face card. So that's going to be 1 minus 12 over 52. And that's 76.92%. So either I could say it's 1 minus this probability, or I could count all of these up. That's 1, 2, 3, 4, 5, 6. Yeah, so 10, 40, 40 over 52 gives you the same response. Any questions about these? These are pretty straightforward but common examples of doing probability, especially with a giant sample space like this. It says now let's use our counting techniques from the previous section to find out some other probabilities. For example, here it says in drawing 3 cards from the deck without replacement, what is the probability of getting 3 spades? It says round to 6 decimal places. Well, what are the total outcomes? It says without replacement. So the bottom of this is going to be 52 times 51 times 50. And the top is 3 spades. How many ways are there to get 3 spades? Well, there's 4 spades total. And I'm choosing 3 of them. The permutations don't matter. So the order doesn't matter here. I'm simply picking that. So this is going to be 4 choose 3, which again, that's the notation I like to use. This is the same thing as 4 choose 3. So I could put that in my calculator. I find out what 4 choose 3 is. That's 4 over 52 times 51 times 50 is 132600. And 4 divided by 132600 is very small, 0.00003. and then times 100. So here 0.00030%. So there's a very, very small chance if I randomly started picking cards out of a deck of cards that I get 3 spades. A very slim chance. And again, the counting principle here was that I had to recognize that the way to choose a hand of 3 cards or 3 spades is all the ways I can choose spades. Like I'm taking all the spades, choose 3. If the example was instead, how many ways can I draw 2 6s, for instance? There's 4, choose 2 on the top over 52 times 51 on the bottom, because I've taken 1 out without replacement. Another example here says a college board has 10 men and 6 women. If a committee of 4 are chosen at random, what is the probability that it will contain 2 men and 2 women? Cool. So this is a little more complicated one. We want the total number of outcomes. This is 10 men and 6 women. That's 16 total. Yep. 16 total. And I'm choosing 4. So the bottom is 16, choose 4. Do y'all prefer this notation or this notation? Or this one?
Yeah.
That makes more sense. This one looks like a fraction, so I get how it can confuse you. I also get confused by that when I use it in my research. So 16, choose 4 possible ways I can make a committee. Then 2 men and 2 women. Well, how many ways are there that I can choose 2 men? That's 10, choose 2. And how many ways can I choose 2 women? That's 6, choose 2. So that's all of those. I then find out these numbers. 10, choose 2 is 45. 6, choose 2 is 15. And 16, choose 4 is 1820. This is 45 times 15 divided by 1820. So there's a 37.09% chance that it will contain 2 men and 2 women. Which kind of makes sense. It leans heavily towards the men's side. So the odds that it's going to be split evenly are not 50-50. If instead I had 6 men and 6 women, then the odds would be 50% chance that would split up evenly. That's all I have for y'all today. Again, the homework for this is open, and I have it due, what did I say, next Wednesday. Part of this will be on the quiz, but it's going to be very, very basic problems like rolling a dice or picking cards or something.
So the quiz, 7.4 and 8.1.
Yes, the quiz will be 7.4 and 8.1. So yeah, the quiz will cover sample spaces and then permutations and combinations. And counting will be on there, but that's kind of implied from that. Whatever you knew from the quiz beforehand, you'll have to know that for this quiz. It's like all the math builds on top of itself. So just be comfortable with that, but you won't need to be like 2-2 with sets or anything like that. So there's not going to be specifically a question about sets or anything like that. It's going to be stuff from 7.4 and 8.1. Those are built off of the previous section. Yes. Yeah. Were you able to get into the homework after that? You're good. If you're not able to get into it, let me know. If you are, and then whenever you finish, let me know off the top of the way.